In this lesson, we are being introduced to the birth of quantum physics and the end of classical physics or Newtonian physics. So everything up until now, light was a wave, which classical physics expressed and described greatly through experiments and math. But a problem emerges, and the only way to solve this was through quantum physics. So what is the birth of quantum physics? Well, here we are entering an interesting part of physics. For so long, light was believed to behave like a wave, propagating through space at tremendous speed, reflecting off of surfaces and being refracted by others. Then along comes Max Planck, Hertz, Einstein, and Compton, who proposed some very different theories about how light behaved. Let's begin about talking about objects that get heated up. We know from past experiences that as objects become hotter, they start to glow. Take a look at your stove. As soon as you turn on the burner, as you wait, when it gets hotter, it starts glowing brighter, brighter, and brighter. If you ever heat up metals, they get brighter, brighter, and brighter as energy increases. Same thing with old incandescent lights. They get brighter as the heat increases, which is energy. So other examples could be heating of steel, low temperatures the human eye cannot see. But let's think about it this way. Can you tell visibly that the stove burners are on when they are very low? So at setting 1 or 2, are they on? We cannot visibly see it, but if I put my hand over top of it, I can feel the electromagnetic radiation coming off. So we cannot visibly see the electromagnetic radiation at low temperatures, but we can feel it. Now, as you continue to heat steel, it starts to glow. This initial glowing is indeed visible, and continued heating would produce all the visible colors of the magnetic spectrum, as well as some infrared radiation. And if the heating continues, it could produce ultraviolet emissions. Thus, as heating continues, the temperature rises. Electromagnetic radiation shifts to higher frequency. This statement in itself is not bad for the wave model of light, because the light emitted had higher frequencies and smaller wavelengths, therefore this is no problem. The big problem with the wave model of light was that if the heating continued, shouldn't the frequencies continue to rise? Or the wavelengths shorten? And thus the brightness of the glowing object continued to get greater. Well, if any of you have turned on your stove, it only gets so bright as we continually add more and more energy to it. It stays so bright, it doesn't get brighter. Why is this? Now, therefore, what was actually observed in the experiments showed a limit to the intensity of the emitted light, which creates a problem. So now we have a contradiction between classical physics and what is happening. So according to classical physics, as we increase our frequency, our energy should increase as well. So here, my energy is increasing exponentially as my frequency increases. But when we did experiments with something called blackbody radiation, that did not always happen. Here's another graph, the exact same, except we're looking at wavelength. So as wavelength shortens, my energy should go up. So classical physics would show a curve that looks more like this, and keep on going up and never come back down. But that does not happen through experiments. So what is blackbody radiation? Well, let's look at it this way. If I was to go outside with a white shirt and it's nice and sunny like I'm wearing right now, it would be nice and cool. But if I went outside with a black shirt and the sun's rays are hitting on me, what's going to happen? I will feel very warm very fast, because the visible light, electromagnetic radiation, is going to be absorbed by my black shirt, which will then cause me to be warm, and I'm going to feel that energy. So all colors reflect radiation except for black. And it's hard to get exact black. If it was pure black shirt, I wouldn't really be able to see it because it's still reflecting some light in the black spectrum. So that's why we call blackbody radiation, because we want to have the absorption of all the radiation. Okay, and that's why these are called blackbody radiation curves, because black absorbs energy. So let's look at this here now. This curve, this little graph here is very interesting. So right here I have 300 degrees Kelvin, and at 300 degrees Kelvin I don't see any energy. All we have is infrared, and only infrared's given off. Now all of a sudden I'm going to 400 degrees Kelvin, or 4000 degrees Kelvin, and as soon as I go to 4000 degrees Kelvin, I get right here almost everything is in the red. So I'm going to get a little red spectrum. That's when we see our metals or something heated up to be red. Now, when I go to 5000 degrees Kelvin, we're going to see this color spectrum there. So now we're going to get something that is a bit more orange. So I'm going to have now an orange spectrum right here. Going up here, it's now going to look orange if we combine those colors. Then when I get here, well, we have orange, yellow, and some green. This is going to, or orange, red, and green. This is going to start providing us with a yellow spectrum. So we can see it going yellow. So that kind of explains things. And then eventually here, once we get all the way over here, this is where we see a blue light. Actually, it might be over here. Here we might see a blue light, but it's almost white. Okay? For a bit to the side, it's going to be white, and then it goes blue, because we're seeing all of the energies. So I'm going to go here and get a white light. So this here would create a very close to a white light over here, and then over there is going to be slightly tinted blue. So that's a general idea of blackbody radiation. An oven is the perfect example of blackbody radiation. So basically in the oven, if we close the oven, it is dark, there's no light in there, and then we turn on, and if we had a camera in there, and then we turn on the oven, we're going to see it eventually, our filaments get turned color, right? And they're going to change to these colors depending how hot it is, the filaments, and that's what helps us with blackbody radiation. Now, the problem here is this, as we see, it goes on forever. So we needed someone to figure out why this happens. So along comes Max Planck, who describes why our curve looks like the actual experimental blackbody radiation curves and not like our classical physics curve on what it would predict based on all of our classical physics that we learned so far. So Max Planck said that vibrating molecules in heated material can only vibrate with specific quantities of energy. And when the energy radiates out from the material, it is not in the form of wave, but in bundles of energy called quanta. This here is very different from the waves. He says they're not waves, but they're quantas, little energies of quantas, packets of energy. Now this confused a lot of people because, well, through all of our experiments, we've shown that light is actually a wave. So here is his formula. He has energy is equal to the number of photons, or number of quantas, multiplied by Planck's constant, which is, Planck's constant, which is 6.63 times 10 to the negative 34 joules seconds, multiplied by the frequency. Now, if it's little packets, you would expect this to have, or little quantums, or quantities, you'd expect this to be more of a staircase. But if we look at how small this number is, it's so tiny that this actually is a little staircase, but the increments are so small it looks like a straight line. So these theories of quanta help describe why our blackbody radiation curves would drop down like this instead of going exponentially up. And why as we increase the energy didn't necessarily mean we got so much more ultraviolet radiation and so much more gamma and X-ray radiation. There was still more of it, but it wasn't like we had a whole abundance more of them. Now, this theory of quanta was hard to accept because it challenged the idea that light behaves like a wave, and it challenged the classical physics of Newton, since it proposed that a physical object is not free to vibrate with any random energy. The energy is restricted to certain discrete integral values. So when we think about that, our quantities, we can't have half a quantity. It has to be a full quantity. So it's only whole numbers that n value. It took much more experimental evidence for this theory to become widely accepted. So there's two ways we could calculate it. Here's the formula on your formula sheet. And then we could also do something like this here. So I could replace this here in for, my frequency. So I could also write it as energy is equal to my Planck's constant multiplied by my speed of light, or electromagnetic radiation, divided by my wavelength. So let's try our first example here. We want to calculate the energy of a quantiphoton of blue light with a frequency of 6.67 times 10 to the 14 hertz. So let's go with what's known first. We know Planck's constant is equal to 6.63 times 10 to the negative 34 joules seconds. We also know my frequency in this case is equal to 6.67 times 10 to the 14 hertz. Okay, now hertz is also equal to seconds, the arc seconds, okay? Well, for this now, I'm just going to use energy is equal to Planck's constant multiplied by my frequency. So in this case here, the energy of each photon of blue light, for each one, we're going to assume n is 1, is going to be equal to 6.63 times 10 to the negative 34 joules seconds multiplied by 6.67 times 10 to the 14 seconds to the negative 1. What we end up getting here is 4.42 times 10 to the negative 14. Now I look at this, we have seconds cancel off, so we're left with energy, which is joules. Now let's try my second one here. We're going to look at a quanta of red light with a wavelength of 6.3 times 10 to the, or 6.3 times 10 to the negative 7, or in other words, 630 nanometers. So for my second half, we know my wavelength is equal to 6.3 times 10 to the negative 7 meters. We know my Planck's constant is 6.63 times 10 to the negative 34 joules seconds. And we also know my speed of light. So in this case, I'm going to use this formula here, Planck's constant, and since we don't know frequency, I'm going to substitute frequency for c all over lambda. Okay, speed of light divided by my wavelength. So here I'm going to end up getting 6.63 times 10 to the negative 34 joules seconds multiplied by 3 times 10 to the 8 meters per second. And all of this will be divided by 6.3 times 10 to the negative 7. So we end up getting 3.16 times 10 to the negative 19 joules. Because here we look at this, meters cancel, seconds cancel, we're left with just joules. And that will give me the energy of the red light per photon. So here are some questions for you guys to do by yourself. Alright, so let's try example 2 here. Your eye can detect as few as 500 photons as light. So we have to have a minimum of 500 photons. The eye is most sensitive to light, having 510 nanometers wavelength. So what is the minimum amount of light energy that your eye can detect? So this is what we're given. Okay? Now, we're looking at this here. I'm going to use this formula instead of this one because I know my wavelength and I know my speed of light. And we don't know frequency. So I'm automatically going to substitute my frequency formula calculation into there. So if we look at this, I'm going to end up going, I'm using this here. We have is equal to, I'm going to plug in, we have 500 photons multiplied by 6.63 times 10 to the negative 34 joules seconds multiplied by 3.8 times, or 3 times 10 to the 8 meters per second. And all of this is going to be divided by 5.1 times 10 to the negative 7 meters. Now I end up getting, when I calculate this, 1.95 times 10 to the negative 16. Now let's see my unit cancellation, see if we get joules. So we have seconds, seconds cancel off, meters divides meters, so I'm left with just joules. So then, the minimum amount of energy our eyes can see we need is for 500 photons is going to be 1.95 times 10 to the negative 16 joules. So here are some little questions for you guys now to try do yourself. So in our last question, we have how many photons are emitted each second by a laser pointer that has a power output of 0.4 milliwatts, if the average wavelength produced by the pointer is 600 nanometers. So let's first look at what's given here. I have my wavelength is 600 nanometers. I have my power is 0.4 milliwatts. But in our formula, we want energy, right? So if we look at my formula here, we're looking at energy, and this wants to know how many photons. We don't have power. Well, we know that 1 watt is the same thing as 1 joule per second. We also know here, therefore, we could say that in 1 second, and we're looking per second, we emit 4 times 10 to the 4 joules of energy. So in other words, we are ending up emitting, since we're looking at a milliwatt, we end up emitting 0. My energy is going to be 0, because it's milliwatts, 0.00 joules of energy per second. Okay, this should be to the negative 4, by the way. Made a little mistake there. So, now that we know that, let's try and solve this question out. So I'm going to use, once again, this formula right here. So, and I must rearrange this formula because we're trying to figure out my number of photons. So I'm going to rearrange that so I get N is equal to my energy multiplied by my wavelength divided by my Planck's constant multiplied by my speed of light. Right? So now we're going to plug in everything we know. I know we have 4.0 times 10 to the negative 4 joules multiplied by 6 times 10 to the negative 7 meters all over 6.63 times 10 to the negative 34 joules seconds. And then we're going to multiply that by 3 times 10 to the 8 meters per second. Okay, so once I calculate this, I'm going to end up getting 1.21 times 10 to the 15 photons per second. Well, why do we have that? If I look at this here, we end up getting, we have joules cancel with joules, we have meters cancel with meters, and then we're going to have seconds cancels with seconds. So he ends up getting this many photons, and if we look at the question, it wanted to know how many photons are emitted per second, so that's why we end up getting this many photons per second. So now I want you guys to do these two questions, pause the video, and see if you get the right answers. This last little bit here is a table that I suggest you guys understand a little bit and go over yourself so you understand the different types of wavelengths and what they're common to and the ratios, stuff like that, because it is very important to know for your provincial diploma. So this table here,